Well, I'm very happy to be here tonight and that you've taken the opportunity to come and learn a little bit about the Large Hadron Collider. I know that your other option tonight was to watch the Barca match, and we'll see at the end which would have been more exciting. So I'm here to talk about the Large Hadron Collider and also the research that I do on the Large Hadron Collider. And the research I do is looking for a particle that you've probably heard of called the Higgs boson. And I assume that most of you are actually engineers and not scientists, and you might be thinking, why have I come along to a science lecture to learn about the Higgs boson? Well, there will be a little bit of engineering, but I'm not an engineer, so I'm going to focus on the science. And I want to start with the question, why should you guys in the audience care about the Higgs boson? And actually, the answer's there. This is the sun. And if it wasn't for the Higgs boson, or something very like the Higgs boson, one problem that we wouldn't be able to answer is, why is the sun still here? And the fact that the sun is still here, up in the sky, burning slowly, and this is the key thing that the Higgs boson helps us explain, burning slowly enough that energy comes down to Earth at just the right rate to keep us warm, to make the plants grow. We need the Higgs boson to explain why the sun burns so slowly, and we'll see why soon. Okay, so what am I going to talk about? Well, I'm a particle physicist, so we need to do a little bit of particle physics. So we'll start with the particle physics, and we'll explain why we need this thing, the Higgs boson, to help us understand particle physics. And then once we know why we need it, I'll give you a recipe how to find a Higgs boson. Then we can talk about the Large Hadron Collider, and this is really the engineering marvel. Unfortunately, I'm not an expert on the Large Hadron Collider. I do the Higgs boson finding bit, but I use this magnificent tool to help me do the physics. And then we'll see the results that we've got, and finally, if we have time, we can have some Higgsteria. Okay, so particle physics. What is particle physics? So particle physics aims to understand the universe on the smallest accessible length scales. So basically we're looking at the very smallest things that we can identify and measure, and we're finding out all about them. So it's the smallest components of matter. We call them the fundamental particles. So fundamental because we can't divide them into anything smaller. And they're essentially just what makes up you and me and the sun and the rest of the universe. So we look for these fundamental particles, and what's also very interesting is to see the way that the particles interact. So there's two things that we need. We need both what makes up you and me, and we need to see the way that they interact. So let's go and look at the particles. So we'll start with something that hopefully is familiar to most people in the audience. This is an atom, which I've blown up several times. An atom is about 10 to the minus 8 centimeters, or I always remember as an angstrom, which is 10 to the minus 10 meters inside. And as I'm sure most of you know, the way that we understand an atom at the moment is that it has a nucleus in the middle, and orbiting around the nucleus are electrons. So I'm going to go over here. So here's the electron. So the electron, we have tried to measure the size of the electron and failed. So we know it's less than 10 to the minus 16 centimeters. Now, we believe all the investigations to date tell us the electron is a fundamental particle. You can't break it up into anything smaller. And actually, it's one of a class of particles we call leptons. So there's a bit of nomenclature here. But really, if I start saying the word lepton, please just think of an electron. So these are fundamental, and you'll see I've got some other leptons here that we found, which are heavier than the electron. But as far as we understand, they're all fundamental. So let's go back to our atom here and have a look at inside the nucleus. So the nucleus, as I'm sure a lot of you know, is made up of protons and neutrons. So protons and neutrons here are bigger than electrons. We've managed to measure their size. And what we understand now from doing lots of particle physics experiments is that they're actually made up of smaller particles that we call quarks. So you see that a proton, or indeed a neutron, is made out of 3 quarks. So you see there's 3 little blobs here. And we've given them all silly names, which are here. So these stand for something. So let me come over this side again. So we call this up, down, strange, charm, bottom, and top. Or sometimes people call them truth and beauty. But they're just fun names. We have to call them something, so that's what we call them. And what we know now is the protons and the neutrons are made up just of these ones, the up quarks and the down quarks. If you put 2 up quarks together and 1 down quark, you make a proton. And if you put 2 down quarks and 1 up quark, you make a neutron. So that's what we're working with. So these are the fundamental particles. And they're grouped into these 2 kinds called leptons and quarks. But leptons and quarks, at least the electron, the up quark and the down quark, are what makes up atoms. Every atom in your body is made up of these fundamental constituents. So all we're doing is looking at what we're made of. But I said the other piece of the puzzle, the other really interesting part, is thinking about the way that these quarks and leptons interact. And this is very important. So the interactions of the quarks and the leptons are governed by 4 different forces. And again, we've given these names. The first one, which is the strongest force, is the strong nuclear force. So what does the strong nuclear force do? Well, it's very handy. It helps the quarks stick together to make protons and neutrons, which is why you don't have to worry about quarks in your everyday life. Well, I guess you don't worry about protons and neutrons too. But they're stuck together by this strong force. It's very strong, and it keeps the quarks all together to make protons and neutrons. We then have the electromagnetic force. And the electromagnetic force is also a very handy force. I can demonstrate here. I will now drop this marble onto the floor. And you see it hasn't gone through the floor. And that's the electromagnetic force. Now, how does that work? Well, this marble is made of quarks and leptons. Specifically, around the edge of the marble are lots of electrons. The carpet is also coated in a layer of electrons. And electrons have an electric charge, and it's the same electric charge that's on the marble and the carpet, and they repel each other. So this is why, when I drop the marble on the carpet, it doesn't just keep going all the way through. The carpet repels the marble. And that works generally as long as you don't have something not too heavy. Then we have something called the weak nuclear force, and this is the one that takes place in the sun. So we'll talk about that a bit further on. And finally, we have gravity. I've already demonstrated gravity. Gravity is the reason the marble drops down in the first place. Gravity just says that massive objects like marbles and the Earth are attracted to each other, and so they move together. So I've demonstrated 2 of the forces for you, the electromagnetic force and the gravitational force. These are ones we experience every day, even if we don't think about it. And the reason that we experience those 2, the electromagnetic force and gravity, is that they can interact over long distances. The strong and weak forces are only felt over very, 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 very short distances, which I've written down here. This is 10 to the minus 17 meters. So unless you're close enough to something else, 10 to the minus 17 meters, you do not have to worry about the strong nuclear force or the weak nuclear force. But when I'm doing my experiments with these tiny particles, I do get that close, and then I have to worry about these 2 forces too. Okay, then there's another part of the mystery that I won't explain, You just need about 4 years study of quantum physics to understand, which is that these forces actually have a particle associated with them, which helps the force be transmitted between the quarks and the leptons. So we have funny names for these too. One of them is called the gluon. So obviously it sounds like glue, and it's the one for the strong nuclear force that sticks together the quarks inside the protons and the neutrons. We also have photons. So photons are light particles, and they transmit the electromagnetic force. We have unexcitingly named W and Z bosons. These are my favorites. These transmit the weak nuclear force. And then hypothetically, we have something called gravitons, which would transmit gravity. And I say hypothetically because nobody's seen these yet. But here they are here, the force-carrying particles. So if we put together the particles that we've seen, the quarks and the leptons that make up inside the atoms, and the force-carrying particles, and then we add in some physics. So we're going to add in Einstein's theory of special relativity, which just describes what happens to physics when things are going very fast. We add in some quantum physics, which is the physics of very small things. And we add in symmetries. So symmetries we observe in lots of different areas of science. We add them in to the particles, and basically we have a model now of how particle physics works that we call the standard model of particle physics. And if you go and have a look on the internet for particle physics, I'm sure you'll see a table very like this with all the different particles and the force-carrying particles that we've seen. So this isn't something that someone just invented overnight. This took the best part of 100 years to come up with from experimental observations and trying to understand what we've seen. And it's possibly now the best tested and validated theory in physics. One of my colleagues said to me once, "Nothing has been measured to 5 decimal places." And I had to explain to him that there's one quantity that we measure to 11 decimal places, and it's only the 11th decimal place that doesn't agree between the theory and the experiment. But I want to talk a little bit more about the W and Z bosons, because this is why we need the Higgs boson. So the W boson, the effects of the W boson were known since about the 1930s, and it was Enrico Fermi that first came up with a theory that said we need something very like this particle called the W boson. And then finally, just 30 years ago in January, the W boson was discovered by these 2 experiments at CERN. They're uninventively named UA1 and UA2. It stands for Underground Area 1 and Underground Area 2. But these were discovered at CERN and really validated this idea they had of this model, the standard model of particle physics. And then, although it's not kind of key to the story I'm trying to tell here, they also found this particle called the Z boson. And it was found, or at least the effects of the Z boson were first found in this detector here at CERN, which is now outside in the museum at CERN, called Gargamel. And when I told this to my students, they pointed out that Gargamel is the baddie in the Smurfs. Anyway, apparently Gargamel is Gargantuan's mother in some novel, and Gargantuan was the experiment they had first, so Gargamel was even bigger. And then the experiment that discovered the W boson a few years later also discovered the Z boson. Okay, so sorry, that was a lot of physics to take in at once. That's the most complicated I hope it's going to get. But why did I want to tell you all of that physics? Well, I wanted to tell you about the W bosons. And the thing about the W bosons, unlike all of the other interactions, is that they can change the nature of particles. What do I mean by that? Well, they can turn protons into neutrons and vice versa. Now, none of the other forces that I talked about, the strong nuclear force electromagnetic force or gravity has the power to change one kind of particle into another kind of particle. It's only, am I still on the mic? It's only the W boson. And this is how nuclear fission and nuclear fusion take place, because they can change one kind of particle into another kind of particle. And that's really key. So what happens in the sun? So the sun is made of hydrogen and helium. And what the W boson can do is it can turn a proton into a neutron. And if you know, you might know that the proton has an electric charge. We'd call it +1. And the neutron has no electric charge. We'd say the charge is 0. Now, when there's an interaction takes place, it's very important that the electric charge is always the same on both sides of the equation. So it means, as well as turning into a neutron, something else would have to be emitted. And what's emitted is an anti-electron. So an electron has charge, we call it -1, and an anti-electron is the opposite of that, it has charge +1. And then, just to balance things off, we have another particle which is neutral emitted called the neutrino. But it basically means, if we can turn a proton into a neutron, it means we can turn 2 hydrogen atoms into a helium atom, as long as we emit an anti-electron in this neutrino. So we can manage to change hydrogen, sorry, I've got this slightly wrong, hydrogen into deuterium. So I read that wrong. So this is 2 hydrogen atoms. One of the hydrogen atoms, which is a proton, the nucleus is a proton, turns into a neutron, and then the proton and the neutron combine to make a heavy hydrogen atom. And then the heavy hydrogen atom can interact with another hydrogen atom and make helium. So what we have is hydrogen turning into helium. But the really key part is we have to be able to turn the protons into neutrons for this process to take place. So the W boson is the one that facilitates this happening, the protons turning into the neutrons. And one thing about the W boson is it's actually very heavy. It's about 80 times as heavy as one of these protons or neutrons. And because it's very heavy, it means that this process here happens slowly, much slower than you would possibly expect, and slow enough that the burning of the sun burns for us at just the right rate to keep us all alive on Earth. So this theory makes a lot of sense, but one mystery stood out when they were looking at this, which is, why is the W boson heavy? And another question is, why is the Z boson heavy? If I go back here, when I introduced the different particles that carried the forces, the photon is massless. This one here, the gluon that transmits the strong force, is massless. But the W and Z bosons are heavy. And not just a little bit heavy, they're very heavy. And this was a bit of a mystery until 1964, when 6 gentlemen, all in the same hot summer of 1964, came up with an explanation. And what they did was they added an extra term into the theory, which I've written down here. And I have brought along a demonstration. So this equation here describes this potential, we're going to call it, but basically a surface of this shape. We often call it the wine bottle potential. So the important thing is that it's symmetric. Remember I said that symmetries are a very important part of the problem. So if I turn the bottle around, at least the bit in the bottom always looks the same from almost any direction. but also that it has this wee dimple here. And I could do with a volunteer from the audience. Excellent. So here's the wine bottle, and I'm going to drop in a marble, a second marble. Now, the most symmetric thing that would happen, if you think about it, is that the marble would go to the top of the dimple, because then when we turn it round, it would look the same from every direction. But as expected, it doesn't do that. Instead, it goes down to the lowest point in the potential. So instead of choosing the most symmetric place, it's chosen a place where the symmetry is, we call it broken, because now when I turn it round, the bottle doesn't look the same from every point, because the marble has chosen one particular place in that circle to go. And so that's exactly what that potential does, and we call it symmetry breaking. We also sometimes call it the Mexican hat potential, and actually this is Flavia, she's one of my postdocs, explaining how it works here. So this is Professor Higgs, and actually you see that he's written down his theory here. You can see his wine bottle potential, and there's a few more terms in his equation. In 1964, like I said, there were 6 gentlemen that thought about this idea, but my old physics professor here, Professor Higgs, was the only one to also point out that adding this potential, adding this shape into the theory, would also create a new boson, a new fundamental particle. And in honor of that idea, we call it the Higgs boson. Okay, in case you're not following, let's try one more explanation of the Higgs mechanism. So I know that most of you are going out on Friday night to the IESIS dinner, and so this is a picture of you all having your cocktail before the dinner starts, and you're all free to move around the room. And we call this a field, so there's a field of people, something that's evenly distributed around the room. And then in comes somebody. This is Muffy Calder. She's the Scottish Science Advisor. And everyone wants to speak to her. You've all got a good idea from Muffy, and everybody crowds around Muffy. So whereas most of the people can move freely in the room, Muffy gets stuck. And she gains inertia. It's hard for her to move through the room because she's so popular. And this is analogous to how the particles, the W and the Z particles, bosons, acquire mass. They interact with all the other people in the room. They interact with this Higgs field. And obviously, if there was different science advisors in the room, they might be more or less popular, and they would all gain a different amount of mass. So later in the evening, everyone's had their dinner and they're having a digestive. And this time a rumour enters the room, not Muffy herself, but Muffy has actually convinced Alex Salmond to appoint a Minister for Science and Engineering. This is great news, finally. And the rumour spreads through the room. So there's no one now in this knot of people, but the rumour is being moved through the room. So instead of Muffy gaining a mass, the field, you people in the audience, have yourself gained some inertia. And this kind of clustering of the field of engineers is as if there's a new massive particle existing, and this would be the Higgs boson. So the Higgs mechanism that Peter came up with has 2 ideas. Firstly, it explains why the W and Z bosons have a mass, because things tend to cluster around the massive particles. And as well as that, it explains why there's another particle expected. So the mass can just cluster itself, and this would be the Higgs boson. Why care about the Higgs boson? That really the science is over now. Well, the Higgs boson makes the W boson heavy. And the heaviness of the W boson makes the burning of hydrogen in the sun relatively slow. And the slow burning means the sun will support life on Earth for the next 1 billion years. In fact, the sun will burn for another 3 billion years, but it's going to start burning a bit too fast. Okay, so now maybe you have a flavor of why they came up with the idea of the Higgs boson. Let's see how we do it. How do we find a Higgs? Well, I'll just start with a note on units. Particle physicists don't use SI, System International units. Basically, they're no good for very tiny things. So we typically use for energy units called giga-electron volts, GeV, or tera-electron volts, TeV. So 1 GeV is 1.6 times 10 to the minus joules. 1 TeV is 1.6 times 10 to the minus 7 joules, or about the energy of a flying mosquito. We use a different unit for mass. It's GeV over c squared. And that's about, well, it's 3.1 times 10 to the minus 23 grams. That's why we use 1 here. It's about 0.93 atomic mass units, or roughly the mass of a proton. Okay. It's just because you will start to see some units cropping up. So to just give you a sense of scale. Right, so let's start with a simple recipe here for the Higgs boson, which you can try tonight when you get home. So I'm going to take 2 very high energy protons. I get mine from CERN, but other particle accelerators are available. And you simply smash them together. And then 1 in 100 billion of these collisions will form a Higgs boson. So it's pretty simple, except after we form the Higgs boson decays, and it decays after 10 to the minus 22 seconds. So but you have a moment to catch it. And now what I do to detect my Higgs boson is assemble a highly sophisticated state-of-the-art detector around the collision point that I've smashed my 2 protons together, and then simply observe the particles that were produced when the Higgs boson decayed. And then finally repeat 25 million times a second for about 1.5 years. And you too can have your own Higgs boson. So let's see in reality how you do this. Well, firstly, you need CERN. So CERN is the European Organization for Nuclear Research. It's located at the Franco-Swiss border, just near Geneva. And if you were to drive up to the CERN site, firstly you would see a very unimpressive sign. And you would also see the nice CERN globe here, which hosts one of the visitor centers. CERN itself is an international collaboration, so there's 20 European countries, including the UK, that all pay a subscription, a membership fee to run CERN. So it's not a Swiss lab, it's not a French lab, it is our UK National Particle Physics Lab that we share with another 19 countries. CERN has about 4,000 employees, but what I am is I'm one of 10,000 visiting scientists. The scientists visit from 608 universities and research facilities around the world, including Edinburgh and Glasgow. And CERN basically provides for me and for other scientific users particle accelerators. And there's currently 17 experiments running at CERN. And I work on one of them. So what I use is the Large Hadron Collider. So the Large Hadron Collider, the LHC, is CERN's main activity. And there's 6 of those 17 experiments that use the LHC. So what the LHC does is it takes protons and accelerates them, basically from rest up to very, very high energies. So as of 2 years' time, the LHC will run at 8 tera-electron volts. So tera-electron volts, 1 tera-electron volt was the energy of a flying mosquito. So it doesn't sound very energetic, but a mosquito is something you can see. What's accelerated are protons, which are about 1,000,000,000 times smaller than a mosquito. Where do they get the protons from? Well, you get the protons from a bottle of hydrogen. And here is the bottle of hydrogen that feeds the LHC. A bottle of hydrogen, as far as I understand, is quite a cheap thing to buy if you're a scientist. It's maybe about 200 pounds. And in fact, they have to replace the bottle of hydrogen every year. Not because they've used up all the protons in it, but because the hydrogen gas can escape very slowly out of the cylinder. So what I've put here is to show you, and we will see this a bit later on, that the LHC is part of a complex. It's not just one big accelerator, it's part of a complex, and we'll see the protons have to go through this whole chain of accelerators to get up to this phenomenal energy of 8 tera electron volts, and this is the world's highest energy particle collider. So if you were to go and fly over the CERN site, you would basically see Geneva is down here. This is not a particularly great picture, but Geneva is down here. This is the runway, the airport. This is Lake Geneva and the Alps in the background. And then in the foreground, you would not see this nice red ring, but that red ring indicates where the LHC is. And the reason that you cannot see it is it's underground. This is a picture of the tunneling machine that was used to tunnel the hole. As far as I understand, this was the same kind of tunneling equipment they used to dig the Channel Tunnel, which I guess starts showing my age, that I remember when they were digging the Channel Tunnel. And then down a lot of entrance shafts, they had to drop all of the pieces of the LHC, piece by piece by piece. So what's being dropped here is a magnet. It's 13.7 meters long. It's called a dipole magnet, and that's the main part of the LHC. And then if you were to look inside the magnet, what you would see is not just one magnet, but this is in fact a different kind of piece that was put in from this blue one, but what you see here is there's 2 holes. And the 2 holes are there for the protons. So I have 1 proton going this way, and 1 proton going this way, and they're accelerated, speeded up to extremely high energies, and then they're smashed together. So the LHC is 27 kilometers around. Due to the lie of the land, it's between 50 and 175 meters underground. And the magnets that keep the protons in orbit, there's almost 10,000 magnets. 1,232 are these dipole magnets, this one here. Each of them are 4.3 meters long. What's amazing to me is they operate at a temperature of 1.9 Kelvin, which is just above the coldest temperature you can get, 1.9 degrees above absolute zero. And this makes the area inside the LHC the coldest place in the solar system. It's colder than the average temperature between here and the sun. It is not, I should say, it's the coldest extended place. Other labs have got down to colder temperatures, but it's the coldest 27 kilometer place in the solar system. Now, each of the magnets provides an enormous magnetic field. I don't really have a good idea for magnetic fields. They provide 8.3 Tesla, which is an enormous magnetic field, and they cost, I've put this in Swiss francs, 500,000 Swiss francs each. So building the LHC was an expensive business. But what do you get for your money? Well, you get the ultimate atom smasher. Now, I may have led you to believe that I take 1 proton and 1 proton going opposite directions, speed them up, and bang them into each other. That's not what happens. We take 10 to the power 11 protons, which is 100,000 million protons going one direction, and 100,000 million protons going in the other direction. and smash them into each other. And we smash them into each other 25 million times a second. And we do it at 4 points around the circle. So the point that I work at is, that's a good question. I think it's this one here. But there are 4 points around the circle, here, 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 and here, where we allow the protons, instead of going in those two separate tubes, but we instead, I'm going to put the mic down 1 sec. Instead of them going parallel, we steer them into each other, to crash into each other, to hopefully make our Higgs bosons. So when you have 10 to the 11 protons going one way and 10 to the 11 protons going the other way, the total energy circulating around the LHC is equivalent to an aircraft carrier traveling at around 10 knots in something that's so small that you cannot see it. So it's an incredibly intense amount of energy that's in the Large Hadron Collider. And I tried to look up very quickly what that would be at a Yarrow-built ship, and couldn't quite find out the mass. So how do we find the Higgs boson? So like I said, 1 in every 10 to the 10 collisions, the LHC will form a Higgs boson, and the Higgs boson unfortunately decays very, very quickly. But we have a pretty good idea of what the Higgs boson will decay into. So I've put a whole list of things here, but what's important here is that it decays into pairs of things. And the two that we'll kind of see a bit later on is a Higgs boson decaying into pairs of Z bosons, and a Higgs boson decaying into pairs of photons, the particles of light. And then it's all just a bit of a waiting game. Because it's only 1 in 10 to the 10 that makes a Higgs boson, we have to look through a lot of data before we can even be, see one Higgs boson, and then enough to be sure it wasn't a mistake. So then how do we do it? Well, this is 50 meters underground, actually more like 100 meters underground under the Genevoise soil. And this is my experiment, the ATLAS experiment. This is what it really looks like. This is in fact when they were building it. So it's now, this big hole here is completely filled with the detecting equipment, and you can see someone here for scale. So I was trying to work out for you Glaswegians how big this would be, and I think it's this cavern that this is about the size of the hall in the Kelvin Grove Museum, just stuffed full of detecting equipment. And you can see the civil engineering that's had to go on here to support this absolutely enormous detector. Here's an artist's rendition of it, and here's another picture of it when now they're filling up the space with detecting equipment. There's another picture here, and if you get hold of the slides, you can actually see a nice video there of them building it. But essentially what we've built is the largest and most sophisticated digital camera ever built. So for dimensions, it's 45 meters long, it's 25 meters high, and it's 7,000 tons. However, I'm told that if you wrapped it all in plastic and chucked it in the Clyde, I guess, further out towards Greenock, you need the space, it would float. So who runs this? Well, the ATLAS collaboration run it. The ATLAS collaboration is 3,000 physicists from 175 institutions in 37 countries, including about 25 of us from Edinburgh, and there's also probably about 25 physicists from the University of Glasgow. And here they are having a party with the spare magnets for the LHC in case they need them. They just needed a very big space, and that was one. Now, we're not the only people involved in this business. We have a friendly competitor. They're called CMS, the Compact Muon Solenoid. Their detector's not as big, but it would sink. Here's Professor Higgs visiting CMS. Okay, so now I have a video of how this works. So what I have here is a proton and it's going through the first part of the CERN accelerator called the booster. It's then going through something else called the PS, the proton synchrotron. It now goes through the SPS, the superproton synchrotron, and each time it's getting more and more energetic, and finally it goes into the LHC. So let's go and have a look in the blue magnets here, some graffiti on the wall. And you see we've just crossed the border into Switzerland, my experiments in Switzerland. And here now we have a proton, and you see inside the proton we have 2 up quarks and 1 down quark, and it's going along the accelerator and it's going to meet a proton coming the other way. And it's going to meet right in the middle of the ATLAS detector. And what's happened is it's formed a Higgs boson. We were lucky this time. And the Higgs boson has decayed into 2 photons, into 2 of these particles of light. And then we detect them inside the detector because our detector can detect photons. So maybe, is it worth watching that again? What do I do? Okay. And of course what it's showing you now is 1 proton and 1 proton, but you should remember that each of those protons is in what we call a bunch of almost a billion protons. But it's only 1 that hits with 1 in the other bunch. So I think it looks a bit like fireworks when that happens. But we'd never see the Higgs boson. All we see is the evidence that something came along and made 2 of these photons, 2 of these particles of light. That's all we see. So I said it's a digital camera. Here's an actual photograph from our detector where what we've seen are these 2 particles of light. And you can see they're kind of highlighted here in yellow in this green part of our detector. And this is a map, an energy map of that green part of the detector rolled out, and you can see there's 2 very significant energy deposits. And what we think happened here, but we're not sure, but we think is this time there was a Higgs boson came along and it decayed, it disintegrated into these 2 particles of light. Okay, now we're going to move on to the advanced higher level. The Higgs boson can also decay into 2 Z bosons. Now the problem is the Z bosons also decay very, very quickly. And so instead of looking now for 2 Z bosons, we look for what the Z boson decayed into. So it can decay into an electron and an anti-electron. So I've got 1 Higgs boson, makes 2 Z bosons, and each of the Z bosons decay into an electron and an anti-electron. So now I'm looking for 2 electrons and 2 anti-electrons. And here's another picture where that's precisely what I see. So this time, you'll see the energy deposits are colored red and green, and there is what we call a track leading from the very center of the detector out towards these energy deposits. And you'll see there's 1, 2, 3, 4. It's a 3-dimensional camera, so okay, these guys look very close to each other. If I look in the other view, you'll see in fact 3 of them still in this view look close to each other, but they actually are quite well separated. So this is 2 protons have come in, collided, and what we see are 2 electrons and 2 anti-electrons. So again, this may be the Higgs boson. On the other hand, remember that 99,999,999 times out of 10,000 billion collisions are not the Higgs boson. So maybe this one was the Higgs boson, or maybe it wasn't. And we will never know for sure if each of those pictures we take really was a Higgs boson or if it was something else. However, if we see these kind of pictures enough, we can be sure that a certain fraction of them were from the Higgs boson and the other fraction weren't. But I couldn't tell you each individual one whether it was from a Higgs boson or not. So one final picture. This is another what we call Higgs boson candidate event. Again, where it's made two Z bosons, and this time the Z bosons have decayed into heavy electrons called muons here. And you can see here, this is the middle of the collision with the fireworks coming out, and these red lines indicate where they've seen these muon particles. So that's what we do, 25 million times a second for 1.5 years. And then these are the results. So this is what got me extremely excited. And what you'll see is it's just a tiny little bump on a graph here. And that's because, like I said, some of the time we don't know if it was a Higgs boson, and sometimes we don't know if each individual one we see was really a Higgs boson or not. But you'll see this is the kind of prevailing trend here, and there's a little bump on it. And if I take the prevailing trend off, you'll see quite a big bump. And we believe now that this little bump was caused by Higgs bosons. Now what we didn't know before we started this was how heavy the Higgs boson was, because we'd never seen one before. But now we know it's about 125 times the mass of the proton. So the next thing I'm going to show you is an animation of this data building up over the 2 years that we ran. And it runs a bit quickly, so you'll have to watch. Well, that was it. Let's see if I can run it again. It runs a bit slower on my web browser. But you'll see what happened is as we took more and more data, the black points started adding up. But this little bump became more and more noticeable. So I'll run it once more, and instead, if you can focus on here, which is the difference between the blue line and the red line. So maybe if you're watching, you could see that this bump here started getting bigger and bigger and bigger. And basically when this bump was large enough, that's when we were sure we had found something new, something that looks at least very, very like the Higgs boson. So this one is when the Higgs decays into these two particles of light. We have a very similar plot when it decays into the two Z bosons. And here, what's seen now is something that agrees better with this kind of blue color than with just the red color. So this plot for me is not very convincing, but really what we've seen is we've seen the Higgs boson decay in two different ways, and the two different ways that it was behaving gave us the same result. That the Higgs boson had the same mass in both of those results. So that was the big excitement, and that caused Higgsteria. So really, science is over now. So this all kicked off last year, 4th of July 2012 was the day they had the big seminar at CERN. I was sitting in Edinburgh. I think there was only 4 of us from my ATLAS team in Edinburgh. The rest of them had gone off to CERN or were on holiday. This is the main auditorium at CERN, where the announcement was given. This is one of the spokespeople giving the announcement. This is the queue to get into the main auditorium, which I'm told if you weren't in the queue by about 3 the morning before, you wouldn't get in. And this is Peter and my colleague Alan. They reserved him a seat. He didn't have to queue in the morning watching the seminar. And this is afterwards. This is Fabiola Gianotti, that some of you may know. She was the spokesperson of ATLAS at the time, and she's now actually an honorary professor in Edinburgh, and they were excited to see each other. So we were on the front page of every news article that we could look that we could find. We took a screenshot of this. Very excitingly for me, I got onto the telly. So for once in my life, I actually went into the lab that we have in Edinburgh. So we have a lab in Edinburgh because we've actually built, and they're building part of ATLAS for the future. And this is one of my colleagues posing in the background. They were actually doing something useful, but they decided to interview me in the lab, but I never wear a lab coat and I felt a bit strange. And then I got onto late night STV, and this is Dr. Bunhead. He's the guy that lights his head on fire. And my colleague Rick St. Dennis from the University of Glasgow. So that was quite exciting. And then Peter Higgs got some very nice letters. This one is from the Prime Minister. This one is from the Leader of the Opposition. And this one is from the Scottish Government, congratulating him. Got some very nice emails as well. Dear Sir, we are a craft beer micro company and would like to make a brewing special edition, a homage to Mr. Higgs. Firstly, we would like to know if there's any concern about it. And secondly, we'd like to know what kind of beer Mr. Higgs likes. And so they actually made the homage to Mr. Higgs beer, and when Peter went out to Barcelona in, I think, December last year, he tasted it. Said it was very nice. We inspired some nice artwork. So this is a portrait that someone sent us. I'd like to thank Peter with the portrait. We didn't actually get a copy of the portrait, we just got the email. And then finally, we had lots of emails, I just picked a few of them. This is someone who's named their boat Higgs. And they've named it Higgs because, as they've written, this boat was our divine particle, the missing part in our life, which is very sweet. So after that, as a proper scientist, of course, you have to publish. So both ATLAS and CMS published their results. And I've kind of written the key part of the abstract here. So clear evidence for the production of a neutral boson with a mass of 126 with some errors is presented. Right. An excess of events is observed, signaling the production of a new particle with a mass of 125.3 with some errors. Please note that although these two numbers are very slightly different, they agree with each other within the measured error. So they did see the same results. And then we took Peter Higgs to ATLAS. So this is Peter Higgs. This is me. This is Fabiola Gianotti, who was the spokesperson at the time. This is the principal of my university. My boss is not here. I think he's just off the picture. So there was me, my boss, my boss's boss, also off the picture, my boss's boss's boss, and my boss's 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 boss. Oh, went to CERN. And here we're standing at the ATLAS detector. And this is Peter Jenny, who also used to be spokesperson of ATLAS. Okay, so that brings me to the end, except you might be wondering what's next. So this year and next year, the LHC is being upgraded. And the main work that's going on is that all the connections between the nearly 10,000 magnets, the welds, are being upgraded. So here's some work going on to test the strengths of the welds. The ATLAS and the CMS experiments are also being upgraded. So there's been some new detecting equipment added. And this is one of my undergraduate students, Rebecca, who was lucky enough to spend the summer at CERN. And what they're actually doing, it's hidden here, but they are working with the new detector that will actually go right into the center of ATLAS. That's being put down there sometime early next year. And the LHC is going to start again in 2015, and it's going to start with twice the energy, 13 or 14 TeV, the energy of the flying mosquitoes, and will run for about 4 years till 2019. Now, of course, you never want to stop when you have something so brilliant as the LHC looking for your Higgs boson. So if the funding keeps coming, the plan is to further upgrade the LHC and the detectors and run till the end of the 2020s. So that's the LHC. What about the Higgs boson? So the ATLAS and CMS physicists are still analyzing the data that was taken in the last couple of months of 2012. But so far, all the indications say that the new particle we found is exactly as expected. So we now call it a Higgs boson. It looks just like we expected. Why then are we keeping going? Well, the LHC run will allow us to make more measurements, measure more things about the Higgs boson, and measure them more precisely. And only then, when we've made the very precise measurements we want, can we say, if back at the beginning I had the squares and said this is the standard model of particle physics, is it exactly as the standard model predicted? Or maybe, hopefully, it's subtly different. So the kind of message of this is, and obviously I stole this from someone, the universe is full of magical things patiently waiting for our wits to grow sharper. And that was the case in the LHC. You know, it makes the Higgs bosons, but we have to spend lots of time analyzing the data, understanding the data to see the Higgs boson and finally realize for what it is. Of course, I think what we're all hoping is we'll not just have the Higgs boson. There might be other new particles that are still waiting to be discovered by the LHC. So lastly, you know, any scientist is only as good as her team. So all the pictures I could find of our ATLAS Edinburgh team, I stuck here. So you see that some of us are based at CERN and some of us are based in Edinburgh. And we like to wear Mexican hats. Okay, so thank you very much.